Let's go ahead and get started. So today we're actually going to start going into data structures. Yeah. With a linked list.
Yeah. Maracas, right?
Maracas.
Yeah.
But you didn't have any.
No, so I'm just shaking my hands.
Really? Okay. Linked list. I think y'all have used this a little bit in OOP, correct? All right, so we're going to go to actually how they're implemented. I think if you took OOP last semester, we didn't go into the implementation of linked lists, but we will be today. And this should give a good idea of how pretty much the rest of this course is going to be handled. So linked list, we've talked about arrays. What are some issues with arrays that's not nice?
They take too long.
They take too long to do what?
Iterate all the way.
Iterate all the way through, true. We'd like to solve that problem. Unfortunately, that one's going to be a lot harder. So we'll table that for now. What's another issue?
You can't get, like, say you want to get to your element right away. Like, maybe you know where it's at, right?
Well, that's a nice thing about arrays is you can jump to it. You think
I remember just points to the next thing.
Points to the next thing. How about adding something in the middle of the array?
Oh yeah, you can just point up and then point back down.
Right. So in a linked list, it's nice, but in an array, it's time-consuming because you got to move everything over. So that's not very good. Same thing with removing. Hopefully, you all wrote remove, where when you remove an element, you have to shift everything down. Again, that's time-consuming. So we want a data structure that hopefully works better in certain situations. And the first one, well, works better in all these situations, but the first one we'll talk about is a linked list.
In a linked list, can you resize it, change the size of it on the fly?
Yeah, you just append to it and delete from it on the fly. There's no fixed size to it per se. That's nice. Okay, why are you telling me that? Linked list, great, thank you. So a linked list is where we're going to start thinking about something of a node. We're going to see nodes time and time again through the rest of this course, so hopefully this idea will be easy. But a node is just containing some components in a linked list. In a singly linked list, I should say, it contains two components, a data and the address to the next node. So you have data and then some link. What do you think that link is?
Another data, right?
Well, it's an address of the next node, the memory address, so it's a pointer. In C++, it's going to be a pointer. So the link is a pointer. And the data is whatever type of data it happens to be, which we can use templates for to basically specify whatever type we want. So here's a good example using a linked list with integers. The head is going to point to the beginning of the list, so we have 45, and then after 45 you can move over to 65, then move over to 34, and then move over to 76. And the last one is null to specify that the list has ended. So notice we're not storing size per se. We could, but we're not. But we're saying the list is done when you get to the end, aka null. Because the kernel should be at 0, so it's safe to assume that you can't go there. They're just trying to give you an example down head. Maybe it's the beginning is pointing to memory address 1200 or 1200, which is where the value 45 is stored. And then the next memory location might be 1575, so it jumps over there. Notice that these numbers do not have to be contiguous. The pointer could be something afterwards, or it could be something before in the memory space. The idea or the point is that it can point to anything. Thank you. Morning. So node, you can use a class or a struct. We're going to be using classes in this class because it's C++, and we don't need to mess with structure now. All right, so node type. Okay, great. By the way, your lab is to finish our implementation of a singly linked list, which we're going to be doing here in class, and then you get to write the doubly linked list. Just FYI.
Wait, lab is due?
Yeah, the lab that I'll assign today.
Is due today?
No, it's due. Oh, no, I'm sorry. The lab I'm going to assign. Okay, good. I'm glad you're catching on. So y'all are awake. Good. Good. Here's a better example. All right. 4 nodes. So your linked list is going to keep track of the head, and that's a pointer or a link to the first element. And in this situation, the first element is this node that contains the info or the data of 17, and another link that happens to go to the next node. Notice, just for duration, for make sure this is clear, the link going to 2800 might be a node later, but then might go 1500, meaning that the next node is somewhere earlier in the memory address. It does not matter where it is as long as it knows where the next node is located in memory. And then the final link is pointing to null. Okay. Any questions about this picture? Nothing so far? We're good? Okay. Okay, we could create a separate pointer. All right, you know what? That's enough of this. Let's go code. So for this lab, we're on lab 9, right? Good.
Yeah.
Lab 9 would be the next one.
Yeah.
Good. So real quickly, I'm going to kind of combine the lab and the lecture today to give you an idea of what I usually expect when I start talking about a new data structure. That way, moving forward, you can have an idea of what we really need to do to implement and move together. So in this lab, we're going to complete our implementation of the singly linked list. I've put a header file here, and we're going to actually do part of this lab today, and then the rest of the lab you need to fill up or complete.
Thanks, Dr. West.
You're welcome. Don't expect it again. And then 1 is a singly linked list, and then 2 will be the doubly linked list that we'll talk about later. And I have some questions, but we'll get to that in a moment. First off, excuse me. All right, what do we have? So if I were to go in the source, singly linked list.hpp, what have I created here? Well, what is this? What is this code? We talked about templates. What does it mean here? Templates class T, class S, LL list. I'll tell you that singly linked list. What's that template doing here?
Nothing so far.
Nothing so far. Okay. Good question. Oh, it looks like I'm using T down here. I'm using append as well. Insert at the end of a list this value. Okay. Insert at a given position this value. Notice that T I'm using right here. So what does that mean? This singly linked list is a list of T, right? T, whatever T is, maybe integers or doubles or some other class. I have a print function as well. Okay. So as a class exercise, we're going to fill in the private member data for the singly linked list. What do we need to do first?
Size.
Okay, we can have size if you want. So int n size, sure.
Do we need a linked list? Create one?
We are implementing a linked list here, so we are creating the linked list. But what do we need in order to represent a linked list as a class? We can store the size, and that's fine. But what else do we need? We're going back to the pictures is a good idea.
Something with pointers.
Something with pointers. All right, great guess. Yes, sure.
A node?
A node. All right. Have we defined the node?
No.
No, we're going to need to create a inner class here. Class, I'll call it singly linked list node. Oops, I'll make everything public because that's the way we roll. What's the node going to hold? The value. All right. What's the type of the value?
T.
T. All right. Good morning. And what else does it need to hold?
Whatever node comes after that, whatever it points to.
Okay. How do I type that out?
Would be T. And then
We need to. What are we pointing to? That's the first question. What's the link?
T. We're pointing to T, right?
No, we're storing the T in the node. What is the link pointing to?
Another
Memory
node.
address.
Another node.
Yeah.
So the type of this pointer is going to be. No, the T is the data.
Okay. So
It's gonna be a name.
Integer?
It's going to be the node, right?
Oh.
oh, so node's not T.
No, node is something
Okay,
else.
okay. T is just okay.
I may have to template this class in early, but we'll find out. Okay. Anything else we're missing? Well, we've defined the node. That's good.
So do you define the head in that?
Find the head. And what's the head storing? Or what is head's type?
Node.
It's not quite a node. It could be a node. Let's see. So that's all right. But what if the linked list is empty? We don't want to actually create the node
Oh.
right off the bat. So what should this be instead?
Pointer.
A pointer, yes, to the node. That way, we could have head be empty, and that's fine. If head is pointing to null, then that means that the linked list is empty. Right? Okay. Yes. All right. Tab new source. I think I have linked list.cpp. Great. Oh, okay. So I've started to. We have nothing defined. That's perfectly fine. Go ahead and get this guy over here. All right. If we want to initialize an empty singly linked list, what do we need to set? Well, a good way to start with this is, all right, let's see what variables we have in our private data. So we're just going to copy this over. And now the question is, oops, do we need to initialize m size to anything?
To 0?
0, right, because the initial size is 0. Do we initialize m head to anything?
You make it like point to null.
No, right, so that way we're not pointing to anything. Is everyone following me? All right, at this point, we've coded a lot and we haven't tested to see if any of this works. So I'm going to see if it works. Oh, it compiled. Great. Let's go ahead and have main actually create something. So let's do a list of, let's do integers. And we'll create it on the stack. Okay? Now we'll just compile and, oop, there we go. Undefined reference to list. Let's see, then makefile. That's compiling it correctly. All right. So it includes the header file. Does the header file? Yep. Header file includes the CPP file. And if defined singly linked list HPP. There's the code right there. So let's save that just in case that's the error. Nope. Undefined reference. Oh, to the deconstructor. We haven't written the destructor. So let's go ahead and pull that down. Actually, it's a very simple one. Make it empty for now. Compile, good. SL test. Hey, look, it runs. Okay, so it compiles. Good. All right. So the first question here, now let's go back to our header file. We probably want, we'll go ahead and implement get length. That one looks like an easy one. T, scope at get length. All right. How do we calculate the length of our linked list? What? M size? So we're going to keep track of M size. Yes.
Why do we have to use template of class T on every function?
Because every function is templated. So it has to be specified that this function is a template. These functions are being declared outside of the definition of the class. Therefore, the compiler needs to know that this function is a template. C++ has to be verbose this way. So we just return M size. Okay. Actually, let's test that real quick. Let's say SL dot. Oh. All right, compile and run. Hey, good, it's 0. All right, we're doing great. Probably next comes insert at the end of a list. All right. All right. How do we do that? We want to insert this value at the end of the list.
So,
-1, and then just put it there.
Put it there. How do we get to there?
With the pointers? Yeah, pointers.
With pointers.
So get the pointer value from the last node,
All
and
right.
then point to the new value.
Pointer. Okay, so, all right. So what you're saying is, all right, hold on. Get the pointer to the last node. Is that what you're saying?
Yeah, so get the pointer from the last node, then point to the new last node. Does that make sense?
All right. Then point to the new last node. All right. What does that imply do we need to do first?
Increment size.
Okay, sure, yeah. Increment size, great. By the way, notice I'm typing this out, what you're saying, as a comment. If you do this, it'll help you and help me help you as well. Please put these comments in your code while you're thinking about it. I'll be able to help you more. And you'll be able to figure out what you're doing that's right or wrong. Okay. But before all that, what do we need to do? You kind of applied it with number 2, then point to the new last node. So what is it that means we need?
We need to create another last node.
Yeah, we need to create a last node. So let's go ahead and do S node on T. I'm going to call it star new node equals, what do we got? New S node. And there's different ways to do this. Yeah, we'll just do it this way. New node. So let's set its values here, because we need inval. What's inval going to be equal to? So I'm creating a new node, one of these guys, and it has 2 values, mval and mnext. So I need to set those values, initialize them. So what should mval be in this function?
What does inval exactly store?
That's the member value, that's the value of the node.
So it should store
let me write, good, and this will stores pointer to the next node, there. Good point, make sure that's commented correctly. And what'd you tell me to do, Jonah?
That, dang, I forgot what I said.
So it needs to point to the current one. is what I'm
Yeah.
saying.
The inval needs to be the current node that you're at.
Mval needs to be the current node you're at. Mval, well, what's mval's type? It's not a node pointer, it's a T. So it stores the value at the node. So it's storing the value. AK over here, it's storing that 17.
So how do you get in this? So say you're at node 17.
There is no node 17.
You're at position 17.
Yeah, I'm at the first position, which is a node that contains 17. Just trying to make this clear. So let me, maybe another way to look at this. So let's say next we want to do sl.append. Let's append 17. And then the length should of course be 1. So we're right now trying to append the value 17 to the linked list. So in here, val is currently 17. We need to first, you said it but we didn't write it down, first create the new node. Alright, so I've created in memory. Now I need to set its value. What should its value be?
17.
17. And what represents 17 in this function?
T.
No, t is the type, telling that 17 is an integer. Val, there we go. Did y'all see what's going on here? Okay. The other value of node is mNext. Let me show you that. Now, so we have the mval, and now we have mNext. Stores a pointer to the next node. If this node is going to be at the very end of the list, what should it point to? There. Yes. All right. Perfect. Okay. So before we go on, we need to at least think of the corner case. What if there's nothing in the linked list?
Then it wouldn't do anything.
Well, we want to add this to the linked list, right?
Add it there. So you get the head and point it to the new node?
Right. So if the list is empty, just set head. And there's different ways to test this. I prefer to check if head is null. And if it is, head equals new node. Else, then we're going to do, otherwise if that's not the case, then we need to get a pointer to the last node and then point to the last node. Right, and else, and we'll get to that in a moment, because right now we're going to take care of the case is if the list is empty. But what's the last thing we need to do?
Return.
Okay, we could return true. But what's the other thing we need to do? We wrote a comment for that we forgot.
Increment size.
There we go. Okay, let's see if that compiles. We did one thing. Notice we did one thing. Let's go ahead and test it. Uh-oh. Is not a template. That's correct. So we don't need to put a T in there. There we go. Okay. So hopefully head is pointing to the new value. And notice over here we have the link to 0 and the next one is 1. All right. Now we could implement this, but we don't really have a way to test it right now. So we probably want to come up with some way to test it. We need to have some other functionality added to test. We could do print. Now let's do print for now. Print is a good function to write early on because then you can at least diagnose early what's happening, and then after you have at least some basis for your data structure working, then I would add the actual unit test cases where you're getting at different positions. Because then you know at least some functionality is working so your test cases can function. Let's do print because that's always a good test function. How are we going to print a linked list? What do we need to do?
You need to go down the whole list, printing the value in each one.
Okay, we need to go down the list, printing the value at each one. How are we going to do that? A for loop. Okay, great. Let me write that comment that you just said. Go to visit each node, printing the value as we progress. All right, so we need a for loop. Where does it start? Okay. Int I starts at
Head?
okay 0. I is less than size. Okay, I plus plus. All right.
I don't know if you're trying to straighten
Oh, I'm definitely am.
Well, I'm wondering.
it. So is that not the right thing?
Well, because wouldn't it point to null, right? Because I.
Right. This is. I mean.
Yeah, that's all. I was like,
'Cause that-
Doesn't make
yeah.
This assumes we're using an array.
Yeah.
Yeah. So this isn't going to work out.
You could say while in head or while in next is not null.
Okay. While m next does not equal null. I like where this is going. Unfortunately, m next of what? Because that doesn't compile because there is no m next. Oops, initializer before that. Let me jump over here and make sure I type this correctly. Oops. 37. SLS node print. Did I miss something?
The other ones are SLS.
Thank you. All right. mNext was not declared in the scope. Well, that's because mNext is a member of a node. So that's saying, well, which node are we looking at that point, right? What node are we looking at? The head. Well, we'd start at the head, right? Well, we'd start at the head, sure. Okay. While mHead.mNext does not equal null. Okay. Well, if we have an element, that's going to put us in an infinite loop, right? Yeah. But yeah, I think you're thinking along the right track. If we wanted this to go down, what could we do with mHead?
How can you increment in a linked list? How can you get to the next one?
Oh, that's a great question. How do you go to the next element? Yeah, to the next pointer. So I'm going to help move you along here. The thing we're missing right now is creating a rover, and let's start it at mHead. So rover is going to move from one element to the next. So we're actually looking at rover. Moves from one element to the next. Okay. So while rover.next doesn't equal null, notice I initialize rover to start at head, so it's going to start at the beginning. How do we get rover to move from one element to the next?
Set it equal to next.
Set it. So set it rover. You mean?
Yeah.
Okay. Did y'all see what that's doing? Because remember, rover is a pointer, so it might be it's going to be pointing initially to this node, and then to move to the next guy, it just copies whatever that memory address is back to itself, meaning it's pointing to the next node.
So that's how you do it.
Mm-hmm. This is how you do it. Can I turn this into a for loop? Or let's see what the for loop version would be. Okay. Yeah, it actually fit. Which would y'all prefer?
Wow.
Okay. We'll stick with while loop for now. Perfectly fine. We want to visit each node, printing the values as we progress. Okay, so we want to actually print something, right? So what are we printing?
Or the value of the
The value of rover, which is rover and val. And let's go ahead and give a space afterward, comma space, just to give us something. And then to pretty it up. All right. So this is almost correct. If I do sl.print, let's see what it prints out. What should it print out? Error?
No.
What should it?
just 17.
We want it to print out 17. It printed out nothing.
Well, you see.
If we have one element, what is rover's first element pointing? What is it pointing to? Or what is rover's first element dot next? It's already null, right?
Yeah.
So I don't think check is not to see if rover dash in next does not equal no. The check should be what instead? Because the other error here is if you don't have any elements. Oops. When we try and call print before we append anything, what's going to happen? Seg fault. So it's not rover dash im next does not equal null. What do we want to make sure is not null? Rover itself. Oh, there we go. Nothing in 17. All right, we have a way to at least debug what we're doing, and we've showed how you can print off a value.
So that works because on the last time that it iterates through in the last value, it's going to update it
Null
to null.
to null itself, and then once it's equal to null, we're done. Okay. Here we have print. All right, let's go ahead and go back and finish out append. Get a pointer to the last node. How are we going to do that? We know that this list has to have at least one element because we've already taken care of the fact that if it had no elements. So it's safe to assume at this else statement that head is pointing to a valid node. So how do we get the pointer to the last node? Rover. Rover.
Sounds like a dog, you know.
Rover. It's a good way to think of it. All right, go Rover. Get over there. So let's go ahead and create the rover. Where does rover start? In the head. Perfectly. Perfect. So when do we want rover to stop? How do we know we're at the end?
Equals null.
Okay. And how do we increment rover?
Rover equals rover dot next.
There we go.
That.
Just
Wait, while rover equals null, will that?
yeah, that won't. That's not what we wanted. Good catch. While it's not equal null. All right. Is this a pointer to the last node? Will rover after this while loop point to the last node?
It'll be pointing to
To null, right. So this is not quite what we're looking for. Or at least have something that can iterate through it. So it's not while rover does not equal null, it's while what instead? Yep, yeah, there we go. Because once rover dash next equals to null, then we know we're done, right?
So that means rover dot inval is the last value of the list.
Right, now rover is pointing to now rover, oops, is pointing to the last node in the linked list. Then point to the new last node. So how do we do this?
Then point to the new last node.
Mm-hmm.
So you just said, what, new node to equal node?
If we have new node equals rover, that's copying the memory location of rover into new node, and that would completely ignore that new node that we created. So that's not what we want.
So we need to add something.
Yeah, let's go to the board. Oh, right. Because we've done a lot of this pretty abstractly with the code, which is great. That means we're good at abstract thought, but we need to draw it out in boxes so I can show you how this makes answering this question really easy.
Watch the glare. Mind the glare.
Ooh, there it is. I thought you said you were good at drawing boxes.
Oh, what are you talking about? That's a box.
That's not a box.
That is totally a box.
That's one of those sides or two sides.
All right, Claire, M head pointing to, we'll create, we have 4, and we'll have this one pointing to 18, points to ... which eventually points to, we'll have 17 right here, which points to null. So, we have rover at the beginning points to head, and then while rover dash next does not equal null, you keep moving rover down the chain, right? So now we're at the spot where we have rover pointing to this. We have, let me jump back to the code just to show you real fast. We have new node out here. We've created it, but we haven't hooked it up to anything. So we have a new node. Which points to, we'll say the value we passed in was 8, and of course this is going to null. So at this point we have rover pointing to this last guy, and we have new node pointing here. What is it we want to accomplish pictorially?
You want to push up new node right to the end, before node.
We want this arrow to go to here, right? All right, so we want this to happen. How do we get to this pointer right now?
It's rover dot
In next, and what do we need to set that equal to?
New node.
New node. Perfect. Wow, come on, camera. Whew.
that quality though.
That box.
M next equals new node. All right, you see how the picture made that clear, what exactly we need to do? That's why we need boxes. They're going to become good at boxes, trust me.
So then do we need to set new node dot index to be null?
We already did that up here. Good catch. We did it right there. Anything else?
No.
No, I think this is going to be pretty good. Let's go ahead and test this a little more. So we append 17. What other numbers do we want to append?
32.
76.
1738.
You want another 17 in here?
Sure.
Why not? And my last class's favorite number. It's over 9,000. They were really happy about that. All right. Oh, and let's go ahead and get the length and print it out. Actually, we'll print first and then get the length. All right. Oops. Hey, look at that. 17,832, 78, 17, 9,001. Length is 6. Hey, does that look good? It does look good. All right. Yeah. Okay.
So this kind of seems more difficult than using arrays.
Yes, it is.
So how does it help us? Because it's got to be simpler and simpler.
Do we have a fixed size?
No, so it lets us adjust the size of it and it's better performance. Is that what?
Ooh. That depends. Everything depends. Which probably uses memory better?
Linked list.
The linked list.
If I had to guess, I'd say this.
Yeah, the linked list is going to use your memory a lot better in this case, because you don't need to constantly increase the array size or decrease it all the time and figure out what's going on. If you want to add something, you don't have to shift all the elements over. You just add it where it is in place, and that's a lot faster. Although right now we're adding to the end, which makes it slower, but we'll get to a couple other situations in a bit. Okay, I'm going to pause the video here because I want to make sure testing is very clear. So we're going to go into how we can now set up testing for our environment, the unit tests, namely.